Am I audible? Good afternoon to all. Welcome to the third week tutorial of NPTEL course Thermal Engineering, Basic and Applied. My name is Ananthakrishnan. I do this problem solving session as part of my PMRF TA duty. In this week, we will see a few multiple choice questions and a few numerical type questions based on simple Rankine cycle, reheat, and we'll touch upon regenerative cycle in the very basics. So we will actually look into a detailed regenerative cycle in the next week's lectures. So without wasting much time, we can move into the problems for this week. Look into the first question. It's a multiple choice question based on Rankine cycle. Rankine cycle comprises of how many processes and which all other processes. Look into it and try to solve it. This is for an ideal Rankine cycle. So it comprises of four processes. The cycle comprises of four processes. So if you try to plot it in a TS diagram. And you have got a vapor dome. So there will be the first process will be isentropic work input, isentropic process that is in the pump. Then there will be constant pressure heat addition in the boiler, followed by isentropic work output in the turbine, followed by constant pressure heat rejection. So these two are heat input process, heat rejection process, work output in the turbine, and work input in the pump. So these two are isentropic process for ideal Rankine cycle. So therefore two isentropic process, and these two are constant pressure processes. This is a phase change which happens inside the vapor dome. So within the vapor dome, the temperature and pressure remains the same, but in the boiler, we consider it to be a constant pressure process. It's a flow process. And similarly in the condenser as well, we we actually use constant pressure heat rejection process. Therefore, it consists of two isentropic process and two constant pressure processes. So option 3 is the answer. Now look into the second problem. The question says, which of the following statements are true about reheat cycles? Reheat cycle limits the moisture content at the turbine exhaust. The efficiency of the steam cycle always increases after using reheat. The net work output of the steam cycle always increases after using reheat. The expansion of the steam through the turbine occurs only once in the reheat cycle. It can be a multiple select question as well. So multiple answers can be right. Multiple options can be right. There are multiple answers to this question. So which out of the four options are right for this particular problem? There can be multiple answers to this problem. Okay, let's look into the options. If no. Okay, now we can look into the problem. It's about reheat cycles. So if we try to draw a reheat Rankine cycle on a TS plane, it will be quite similar to the previous case, except that there will be multiple stages of expansion in turbine and then multiple reheating. So in the normal boiler, there will be a constant pressure heat addition, and it will reach a temperature, and from there there will be high temperature turbine where the steam will be expanded, and then there will be a further heat addition to the same temperature, and then it will be expanded in a low pressure turbine. So as you could see, this pressure, uh, these two are constant pressure heat additions, but the initial pressure will be quite high compared to the other pressure. So this is a high pressure turbine, and this is a low pressure turbine. And then there will be heat rejection in the condenser. So basically, there are four processes. Okay, so the first option asks whether the reheat cycle will be limiting the moisture content at the turbine exhaust or not. This is correct actually. If imagine the case where there was no reheating, so then the expansion would have happened directly from this particular point to somewhere here. Maybe we can denote it as having a dryness fraction of x1. And in the second case, we can denote it that the dryness fraction will be x2. So if there was no reheating and then expansion in a low pressure turbine, it would have directly come at x1. Because of the x2, because of this expansion in the low pressure turbine due to reheating, after reheating, it will reach a higher point, a point having a higher dryness fraction or moisture mass fraction, higher dryness fraction or quality of the steam to x2. That means that it will be having a higher vapor content compared to the case of x1. So this is right. The reheat cycle limits the moisture content at the turbine exhaust. So making sure that the condensation doesn't happen uh, the condensation doesn't happen in majority of the uh, turbine. So if you have a liquid which is having a higher density compared to vapor, there is every possibility that there will be chances of corrosion on the blades because of its higher density and mass. So the reheating improves the quality of the steam at the exit of the turbine exhaust. So option 1 is right. So that is given. Quality better dryness fraction or a lower. It would be better that I can write as a lower moisture content or a better dryness fraction. That's the first option is right. The second question, the second option is whether the efficiency of the steam always increases after using a reheat. The third one, the net work output of the steam always increases after using the reheat. So we can actually club together these cases and see whether both of them are right or only one of them is right. So what we could see is that after reheating, the total area and in the cycle increases. So what happens is that for a cycle, the cyclic integral of Q is same as cyclic integral of W. So a cyclic integral of Q, since these two are isentropic processes, there is no heat in addition in these three processes. These pump input, uh, the work output in the two turbines, high pressure turbine and the low pressure turbine. So the heat input happens only in these two processes, and heat rejection happens only in these three processes, in these two processes, in this process. So the total area of the cycle that is projected to the entropy curve, entropy axis, the abscissa, will be the total heat input, and that will be same as that of the total work output from the cycle. So what we could see is that compared to a case where there was no reheat, if there is no reheat, this curve would have come from here straight to here. That means that the total area under this curve, under this cycle, will be less compared to a case where there is a reheat. So what we could see from this is that total area under the area enclosed by the cycle, that will be total area enclosed by the cycle. Total area enclosed by the cycle, that will be equal to the net heat input or the net work output of the cycle. So here, since the area increases, the net work output, net heat input as well as the net work output increases. The net heat to the cycle and the net work increases. So work increases. So what we could see is that net work output of the steam always increases after using reheat. That's absolutely a given. Now comes the option 2. The efficiency of the steam cycle always increases after using reheat. So efficiency could be written as work net divided by Q input. So as you could see, work net increases. But what about the heat input? So as you could see, here along with the work network, the heat input also increases. There will be normal heat addition. In addition to that, there will be a additional heat addition in the second process. So these two increases. So we can't say with surety that increasing the reheating. We can't say with surety that reheating improves the efficiency, because it has to account for a compromise between the network as well as the heat input. So option 2 is wrong. We can't always say with surety that the reheat will improve the efficiency of the cycle. No. Last part, the expansion of the steam through the turbine occurs only in the reheat cycle. Only once in the reheat cycle. That's wrong, because we have seen there's a high pressure turbine, and where partial steam will get expanded, and there is a low pressure steam where the remaining part of the steam will get expanded. So option D is wrong. So in this is a multiple select question where option 1 and 3 are right. Look into the third question. The effect of superheating on Rankine cycle efficiency is efficiency increases, efficiency decreases, does not affect the efficiency. Efficiency first decreases, then increases. So it's a straightforward problem. So we could denote for a Rankine cycle or any cycle, the efficiency could be written as 1 minus of T average heat rejection divided by T average heat addition. Imagine a cycle where there is no superheating and everything happens within the vapor dome. And for the same heat, we think that so for now what we do is that we try to simulate another case where there is a superheating. So currently, this is the case where there is no superheating. Everything happens inside the vapor dome in a TS diagram. So and consider a case where we are providing the same heat. So as you could see, as we move higher within the vapor dome, the enthalpy of vaporization term decreases. So correspondingly, what we could see is that this one, and we give a superheating as well. So in that particular case, the average temperature of heat addition will be higher than that of the case where everything is inside the vapor dome. So there is no subcooling as such. So so in this case, the average temperature of heat addition will be T2 compared to T1. T2 will be higher. So TH. So when we operate with the superheating, the average temperature of heat addition will be significantly higher, and that means that the new denominator will be higher and the total quantity will be lower, and efficiency increases. Efficiency increases with the superheat. So that is a concept why people go for superheating compared to operating only in the vapor dome. So in all the cases when superheat is there, efficiency increases. That's a given. Keeping every other component constant. This is a form. This is just a definition. Back work ratio is defined as the ratio of work, net work done to the turbine work, the ratio of compressor work to turbine work, the network, the ratio of the network done to the heat supplied, the ratio of the turbine work to the heat rejection. It's just a formula-based problem. Look into it and try to solve it. So it's just a straightforward definition. So back work ratio is the ratio of the compressor work to the turbine work. Straight away, compressor work is a negative work, turbine work is the positive work. So the ratio of the negative work to the positive work is called as is known as the back work ratio. So this is not actually applicable to the Rankine cycle as such, where the Rankine cycle will be having a pump. But yeah, this is instead of compressor, we could denote it to be a pump as well. So the ratio of the negative work to the positive work, that is called the back work ratio. Look into the fifth problem. What happens to the Rankine efficiency in winters? It improves in winter than that of summer. It improves in summer than that of winter. Is greater than Carnot efficiency is unaffected by climatic conditions. It's a straightforward problem. So you can take into account the general equation of a cycle. So 1 minus of T mean heat rejection divided by T mean heat addition. So what happens in winter? So if I try to draw the schematic of a TS on a TS plane, so this is the condenser, and the ambient temperature, or if the condenser has got a cooling water, which flows in the opposite direction. Uh, the the Rankine cycle, the saturated liquid in the Rankine cycle condenser will be at a higher temperature to exchange heat with that of the cooling water. So the temperature at which it operates depends upon the cooling water temperature. So what happens in winter, the cooling water temperature, incoming temperature will be lower compared to that of the summer. So when the cooling water temperature decreases, correspondingly, the when the cooling water temperature decreases, correspondingly, the temperature at the saturation occurs, the temperature at which the condensation occurs, that will also come down. So, so once it comes down, the total area, occupied under the cycle increases for the same heat input, the net work output increases. That means that efficiency increases. So that's a concept. So basically, the T mean heat rejection decreases, so the efficiency increases. So that is a concept. In winter, the incoming cooling water temperature will be lower than summer. This means the mean temperature of heat rejection in the condenser, heat rejection in the decreases, and that means that efficiency increases in the process. So the option is it improves in winter than that of summer. So this is straight away opposite. That's wrong. Is greater than Carnot efficiency? No, it cannot be because Carnot efficiency is the highest. If is the max is the theoretically maximum, theoretical possible maximum for a cycle. So that is wrong. It's unaffected by no. It depends upon the climatic condition, just as we have seen. So only option one is right in this case. So we just try to tackle these problems in terms of the mean temperature of heat rejection and the corresponding increase or decrease in the efficiency. For a fixed turbine inlet temperature, which one of the following events occur in the Rankine cycle due to increase in the boiler pressure? Dryness fraction increases, dryness fraction decreases, efficiency decreases, dryness fraction remains constant. It's a straightforward problem that could be explained just like the way we had tried to explain uh, question number 2. So just like the way we have solved the problem number 2, we just try to tackle it in terms of the TS diagram. So we are going to keep the turbine inlet temperature constant. So what we could try to do is that this was the initial case where the turbine inlet temperature is kept a constant. And then the expansion happens and the condensation happens somewhere here. So here, this is the pressure at which it operates. So now keeping the same turbine inlet temperature, this is the inlet temperature T1, T high. So we are going to increase the boiler pressure. So this this is a new case where we increase the pressure but keeping the maximum temperature constant. So in this case, this is P2. So P2 is greater than P1. And correspondingly, the point when we do this, the point of exit, the point outlet point of the turbine will be at a lower dryness fraction compared to that of the initial case. So this gives x2 less than x1. So the quality of the steam at the exit, when we do like this, when we increase the pressure at the turbine inlet, keeping a constant inlet temperature, the quality of the steam at the exit of it will be lower. So it's straightforward. Dryness fraction decreases. We just need to plot. We just need to look into the TS diagram and see where the exit of the turbine outlet will be, and it will be at a lower quality. Dryness fraction decreases straight away. That's all. That completes the initial set of multiple choice questions. Now we can look into a few numerical type questions. Look into it. A turbine produces 984 kilowatt of power in a steam power plant. The heat supplied to the boiler is 2400 kilojoule per kilogram. The heat rejected by steam to cooling water is 1916 kilojoule per kilogram. If the pump work required to condense back into the boiler is 16 kilowatt, what the mass flow rate of a steam in kilogram per second is. So the turbine work, positive work is given. Heat supplied to the boiler is given. Heat rejected by steam to cooling water is given. The pump work required to condense back into the boiler is 16 kilowatt. Pump work is also given. Uh, the mass flow rate of the steam we need to calculate. Try to solve. I'll also try to solve it in a minute. It's a straightforward problem. We need to calculate the mass flow rate of the steam. So for a cycle, the net heat output, the cyclic integral of Q for a cycle will be same as that of cyclic integral of W for a cycle. So that means that the heat supplied minus heat rejected is the same as work done in turbine minus work done in the pump. So this could be written as the mass flow rate of the fluid within the cycle multiplied by the heat input, that is given as heat supply to the boiler is 2400 kilojoule per kilogram minus heat output, that is 1916 kilojoule per kilogram. So that will be equal to the turbine produces 984 watt of power. So this is kilojoule per kilogram. This is kilojoule per kilogram, and this is kilogram per second. And minus 984 kilowatt. So this will be 984 into 10 cube watt, and similarly this will be 16 into 10 power 3 watt. So we can denote it by 984 minus 16 kilowatt. So that is kilojoule per second. So everything you can write in terms of kilojoule per second. So we have a kilojoule per second on the right hand side, kilojoule per kilogram on the left hand side. We bring it to the right and we'll get the mass flow rate of the. So the mass flow rate will be equal to 968 divided by 968 divided by 484. So that will be equal to 2 kilogram per second. So that option is option 3. It's a straightforward question. Now we can look into the 8th problem. So this is also a multiple choice question. Yeah, look into it. Which one of the following statement is correct regarding the Carnot and Rankine cycles? The efficiency of the Carnot cycle is lower. In comparison to the Rankine cycle, the efficiency of the Carnot cycle is high and work ratio is low in comparison to the Rankine cycle. The work ratio of the Carnot cycle is higher in comparison to the Rankine cycle. Both the Carnot and Rankine cycles have same efficiencies and work ratio. The class actually began at 4 o'clock. So we had discussed a few problems till now. So now we can look into the remaining part of the tutorial session. Yeah, there will be recording. I am recording it and it will be provided to you by the NPTEL coders. Okay, the question says which one of the following statement is correct regarding the Carnot and Rankine cycles? The efficiency of the Carnot cycle is lower in comparison to the Rankine cycle. That's wrong. So Carnot cycle efficiency will be always higher than that of Rankine cycle. So Carnot is the maximum possible theoretical efficiency that is available within the temperature range. So what we could try to do is that we just try to plot this flow these two cycles, Carnot cycle as well as a Rankine cycle, on a TS plane. So if you try to see, so T and S, this is T1 and T2. The lower temperature will be T2 and higher temperature will be T1. So just remove these two vapor tones and we can try to show that uh, so it could be explained as 1 minus of T2 by T1. That is the efficiency for the Carnot cycle. So higher temperature will be T1 and lower temperature will be T2. So this shows that efficiency of the Carnot cycle is this one. Just remove this vapor dome and we'll be getting the same temperatures. And in the case of the Rankine cycle, if there is a vapor dome, the maximum temperature at which the heat added will be T1, and it's a constant pressure heat addition process. And the lowest temperature of heat rejection will be T2. So what happens is that efficiency of Rankine cycle can be written as 1 minus of T mean heat rejection divided by T mean heat addition. So compared to the Rankine cycle, which operates consistently at a constant temperature process for heat addition, uh, this is a constant pressure process and the maximum temperature will be T1. So for the same heat transfer, what we could see is that the mean temperature of heat addition will be different for the Rankine cycle. So it will be much lower. So mean of heat addition will be lower compared to that of the Carnot cycle, and therefore, since this will become smaller, Rankine cycle efficiency will also decrease compared to the Carnot cycle. So Carnot will be always greater than that of the Rankine cycle. So the efficiency of the Carnot cycle is That's wrong. Efficiency of the Carnot cycle is high. So this part is right. The efficiency of Carnot cycle is high. Then the second part is regarding the work ratio. We have seen what you mean by back work ratio in one of the earlier problems. It is the negative work to the positive work. So negative work can be compressor or pump work, and the positive work will be the turbine work. So what will be the work ratio? Work ratio will be the net work divided by the positive work. So the network will be equal to the work done turbine minus work done pump divided by positive work will be WT. So what you could see is that the work ratio plus the back work ratio should be always equal to 1. So work ratio will be the work net divided by positive work. Back work ratio will be the pump work divided by the negative work divided by positive work. So if you look closely, the work net will be WT minus WP, and the numerator of back work ratio will be WP. So they cancel out each other, and it will be effectively WT divided by WT, this sum. So the work ratio is work net divided by the positive work. So we need to compare between the Carnot cycle as well as the Carnot cycle as well as the Rankine cycle. Now we try to show that in the TS plot once again. So that will be so we have already seen the efficiency part. Now only to check for the work net divided by positive work. The positive work is the turbine work, and the W net is the WT minus WP, or the pump work. So we try to look into the case of these two works. And in the case of turbine, in the case of Rankine cycle, this will be the this will be the turbine work, and in the case of the in the case of Carnot cycle, this will be the turbine work. So we need to compare between two cases to calculate the net the work ratio. So what will be the answer? We already got the first part, that efficiency of the Carnot cycle is high. Work ratio, that is the net work divided by the positive work, is low in comparison to the Rankine cycle for the Carnot cycle. So that is the positive work compared to the positive work, that is a turbine work, the net work will be lower. So that will be 1 minus of WP divided by, you can write it as 1 minus of WP divided by WT. If the work ratio is low, that means that WP will be high or WT will be low. For the Carnot cycle. So as you could see, since this allows for a pump to operate in the case of a Carnot cycle, in order to go between these two points, the Rankine cycle, this is the work done, work required in the pump. This is the work required by the pump or a pumping device in the case of a Carnot cycle. So as you could see, the WP for the Rankine cycle will be lower than that of the WP for the WP for the Carnot cycle. So what you could see is that 1 minus of WP divided by WT. So WP will be low for the Rankine cycle. So this will be WP for the Rankine cycle will be less than the WP for the Carnot cycle. So this is low. That means that always the work ratio is high. And then the other part. So if you try to establish a equilibrium by or an equivalent case by using the same work output case. So if you try to keep the work done on the turbine a constant, and you just compare between the two cases of the pump work. So what we could try to say is that keeping this a constant, WP will be lower in the case of a Rankine cycle compared to that of the Carnot cycle, and because of that, this particular term will be lower and the efficiency increases. So sorry, work ratio increases for the Rankine cycle compared to the Carnot cycle. So you have to try to bring an equivalence between the terms under consideration. So we know that the efficiency of the Carnot cycle will be high, but the work ratio that is defined as the positive work, the net work to the positive work, that will be high for the Rankine cycle compared to that of the Carnot cycle. Efficiency high for Carnot cycle, work ratio is high for the Rankine cycle. So what you could see is that option 2 is right. So this is wrong straight away. We can actually eliminate the options that are available in this case. So straight away you can say that work ratio is low in comparison to the Rankine cycle by the same argument, by comparing between the work required in the pump to operate the input work. So that says that the efficiency of the Carnot cycle will be high and the work ratio will be low compared to the Rankine cycle. Look into the numerical question. This is a first numerical question for this session. Consider a steam power plant that operates between consider a steam power plant operating on the ideal reheat cycle. The steam enters the high pressure turbine at 15 megapascal and 600 degrees Celsius and is condensed in the condenser at a pressure of 10 kilopascal. If the moisture content of the steam at the exit of the low pressure turbine is known to exceed 10.4%, determine A, the pressure at which the steam should be reheated, and B, the thermal efficiency of the cycle. Assume the steam is reheated to the inlet temperature at the high pressure turbine. So the question can be a bit tricky. So I'll try to draw the schematic. Uh, so try to solve it. I'll also try to solve it within a minute. Am I audible? Yeah, so I try to draw the schematic as well as the plot on the plot of the cycle on the TS diagram, TS plane. So so we denote each of these state points at the entry and exit of different units within the cycle. So consider boiler and the input to the boiler comes from the pump. So the input to the pump will be at the state point 1 and exit to state point 2. And then boiler, exit of the boiler at state point 3. It's given the high pressure turbine entry will be 15 megapascal 600 degrees Celsius. So it goes into high pressure turbine at 15 megapascal and 600 degrees Celsius. And then again it will be reheated. And the entry to the low pressure turbine will be at the same temperature of 600 degrees Celsius. So this you can denote as state point 4 and this is state point 5. And the exit of the low pressure turbine will be at state point 6. And then then there will be a condenser heat rejection. So the heat addition Q in and the Q reheat will be here. The Q rejection will be through the condenser. So these are the 6 state points that are associated with this cycle. And if you try to plot that in the TS diagram, the same cycle, there will be 1 to 2 constant pressure. You consider this to be an isentropy process, constant pressure heat addition. Sorry, pump constant pressure input power that is provided in the pump work input case actually. And then the constant pressure heat addition in the boiler to state point 3. And then expansion in the high pressure turbine, state point 4. Then again reheating 5. I can draw the vapor dome afterwards. Otherwise, it can become so confusing. So it expands in the low pressure turbine to the same condenser exit point. 6. This will be state point 6. So this we do not know whether this will be coming inside a vapor dome or not, but for the time being, I'm putting it inside the vapor dome. So if I try to plot it, if I try to put the vapor dome, it's not accurate as such, but it's just a representation of the actual process. So this is not accurate a vapor dome, but to show that this will come reach the saturation condition and then go. So it need not come to the saturation condition as such. Yeah, but we normally we expect this to reach the saturation condition and then go and come back. We have to make the check whether this will reach the saturation condition in the case of high pressure turbine or the exit of the steam in the high pressure turbine will be superheated or saturation condition. So this is just for the demonstration of the representative matter. So the higher temperature will be 600 degrees Celsius. The higher pressure will be 15 megapascal. The lower pressure will be 10 kilopascal. These are given. If the moisture content of the steam at exit of the low pressure turbine is not to exceed 0.9, so we have got an additional information. X6, the quality will be the moisture content should not exceed 10.4. So the quality should be greater than 89.6 or 0.896. So that is the minimum quality that it can have. The quality or the dryness fraction is the mass of the vapor to the mass of the vapor plus steam. So we need to determine the pressure at which the steam should be reheated to. So the same temperature and this pressure, this particular pressure, that will be a new pressure. So we need to calculate the P5 and the thermal efficiency of the cycle. So we have seen in one of the earlier cases that what happens is that the total work input increases as well as the total heat input also increases. But we do not know whether the actual efficiency will increase due to just mere reheating, but definitely the quality will improve. Assume the steam is reheated in the the assumption is that the steam is reheated to the inlet temperature of the high pressure turbine. So basically the 0.5 temperature will be 600 degrees Celsius. That is one additional option, the one additional data they have given in the problem. So we need to actually calculate this by moving from one state point to the other. So we'll use a top-down algorithm where we start from one particular point and we ultimately culminate in the same point itself. Since everything is in a cycle. Okay, so we'll start with 0.6. That is the exit of the low pressure turbine. So we need to calculate the pressure at which the steam should be reheated. So we need to calculate P5. So we need to locate the state point 5. So for that, we know everything about the state point 6. We know the P6 will be equal to 10 kilopascal. And X6 will be equal to, it should be greater than 0.896. So we take the limiting condition of 0.896 and we calculate the S6 from the state point. So from the steam table, we have to look for a saturated water corresponding to 10 kilopascal and the quality 0.896. We have to look for the entropy. Saturated water in steam table. So in the steam table that I'm using, we know S6 will be equal to SF plus X SFG at 10 kilopascal. And this will be equal to 0.896. So that will be equal to SF will be 191.81 plus 0.896 multiplied by 2392.1. So the value will be equal to 2335 kilojoule per kilogram. So that is given. So that is the kilojoule per kilogram Kelvin. Beg your pardon. This is H6, not S. So that's why kilojoule per kilogram. Similarly, we can calculate the entropy as well. S will be equal to SF plus X6 into SFG at 10 kilopascal. So that will be equal to 0.6492. That will be SF from the steam table plus 0.896 multiplied by 7.49. That will be SFG. That is ST minus SF. Entropy at the saturated vapor condition at 10 kilopascal minus entropy of saturated liquid at 10 kilopascal. That is the difference, SFG. Similarly, H will be, instead of S, it will be enthalpy. Sorry. So the entropy of the state point 6 will be in between these two, in between 191.6492 and 0.8. Sorry, 8. It will be in between that. So we'll get it to be 7.36. Will be kilojoule per kilogram Kelvin. That is a unit of entropy. So we know the state point 6 right now. So all the property we know, and these processes, these expansions in the turbine as well as the pumping power or the pumping process from 1 to 2, everything will be isentropic. This is an ideal Rankine cycle. So what we could see is that since this uh, 5 to 6 is isentropic expansion, S5 will be equal to S6 and T5 will be equal to 600 degrees Celsius. So we look into the steam table for superheated steam. P5 corresponding to 600 degrees Celsius and an entropy of S5 that will be equal to 7.368. We'll get the pressure. So that pressure will be equal to 4 megapascal from steam table. And also we can calculate the H5. H5 will be equal to 3674.9 kilojoule per kilogram. So we have got two properties of temperature, temperature and the entropy, and we calculate the we calculated the pressure since it's in the superheated region from the Gibbs phase rule. Number of independent properties required to define a state point is 2, since it is in the superheated region, that is single phase one. So for that we get the pressure of 4 megapascal straight away. So that is the first part. We calculate the pressure at which the steam should be reheated to. We have already got this to attain this point of 0.896. Quality 0.896. We have to reheat it up to reheat it at a new pressure of 4 megapascal. That's significantly lower compared to the 15 megapascal. Okay, so the first part of the problem is over. Now we can move to the second part. The B part of the problem, we need to calculate the thermal efficiency of the cycle. So it's straightforward. We have to calculate the thermal efficiency. Actually, thermal efficiency will be equal to 1 minus of Q out divided by Q in. Q in will be a combination of two heat inputs. One will be in the actual boiler plus one will be the reheating. For this, we need the heat input Q in that will be equal to H3 minus H2 plus H5 minus H4. So that is H3 minus H4, that is the boiler heat plus H5 minus H4, that is the reheat part. And heat output will be equal to H6 minus H1, that is in the condenser. We know the H6 and we know H1 as well. So this straight away we know H6 will be 2335. We have already calculated 2335 and H1 will be HF at the 10 kilopascal, that is 191.81. 191.81, so that will be equal to 2143.3 kilojoule per kilogram. Okay. So Q output we can get straight away. Now we need to calculate the heat input. So in this one we know H4, we calculated it already. Now we need to calculate H4 and H3 and H2. So in order to calculate the point H4, in order to calculate the point H3 minus, I beg your pardon, this is H3 minus H2. Sorry, H3 minus H2. So in order to calculate the state point 2, that is at the output of the pump, we need the enthalpy. So for that, we actually need the enthalpy at the point state point 1. And from there, we can try to obtain it. So state point 1, pressure will be 10 kilopascal, just saturated. liquid condition. So corresponding to that, H1 will be straight away we can obtain from the steam table for saturated liquid 10 kilopascal, that is 191.81 kilojoule per kilogram. And the corresponding, the specific volume will be equal to the specific volume of saturated liquid at 10 kilopascal. That will be 0.00101 meter cube per kg. Now, the most important one, we need to actually try to correlate it to state point 2. State point 2 at the exit of the pump, you know the pressure. The pressure will be at 15 megapascal. One way that, by which we can obtain the enthalpy at the exit is by adding the work input to the pump with the work input at the with the enthalpy of the liquid at the input. So basically H2 will be equal to work in the pump plus H1. This one could be written as nu. So since this is a liquid, we do not expect a change in the volume, specific volume. So we keep it the same, nu1 into P2 minus P1 plus H1. So it will be 0.00101. P2 will be 15 megapascal. So 15 into 10 cube minus 10 kilopascal plus H1 will be in terms of kilopascal, if you write, so this will be meter cube per kg. So ultimately we can get everything in terms of kilojoule per kilogram. So H1 will be same 191.81. So we'll get H2 will be equal to 206.95. So H2 is known. We have already known H5. Now H4 and H3 are remaining. So H4 will be the exit of the high pressure turbine. H3 will be the exit of the boiler. Now state point 3 straight away we can determine at superheated steam at temperature of 600 degrees Celsius and pressure of 15 megapascal, we can calculate the enthalpy. H3 will be equal to 3583.1 kilojoule per kilogram. And similarly, entropy from steam table only for superheated steam for the temperature and pressure input. 6.6796 kilojoule per kilogram. So we know H3 and S3. So this is S3 is quite important because that's the only way we can calculate the state point 4. So the state point 4 we do not know whether this is a saturated point or not. It can be saturated or it may not be saturated. So there are two particular cases. So it take the case when it is superheated and then try to calculate whether the enthalpy that you get for corresponding to the entropy as well as the pressure. The pressure of the, we know the pressure of this process. So the pressure will be 4 megapascal that you obtain from the first part of the problem. And we have an entropy. So correspondingly, we need to calculate the enthalpy. So if this is at the saturated liquid condition at 4 megapascal, we will be getting one enthalpy. And if it must be in a 4 megapascal line. So and you also calculate the entropy and the enthalpy that you get from the entropy you obtained at the point 3. So that will be same as entropy of the point 4 and also the pressure. So these two conditions, these two certain cases you check. One is saturated liquid at 4 megapascal, its enthalpy. And the second one is the enthalpy that you obtain using the entropy of state point 3 and the pressure of the 4 kilopascal. So if I bet both of them will be different. So we can straight away say that the entropy of state point 4, if it was a saturated liquid, it would have been having a entropy at that particular point. If that is different from the entropy at state point 3, you can straight away say that since this is an ideal case, so that is not the case. So the only case that is remaining will be the state point 4 will be somewhere here outside the vapor dome, somewhere here, and it goes like this. The whole process will be like this. Oh. The whole process might be like this. It will be out of the vapor dome, and then it undergoes a reheating. So we compare both the cases. We take the pressure of 4 megapascal and calculate the entropy. If this particular point of state point 4 was at the vapor dome or inside the vapor dome, its entropy would have been lesser than the saturated liquid. And we already know that the state point 4's entropy must be equal to state point 3. So if the state point 4's entropy is greater than the saturated entropy, then we can straight away assume that it will be out of the vapor dome. So by that analysis, I have already done that. We can say that at the state point 4, it will be superheated steam, and for an entropy of S4 is equal to S3 equal to 6.6796 kilojoule per kilogram Kelvin, and pressure of P4 is equal to 4 megapascal. 4 megapascal, the corresponding enthalpy will be equal to 3155 kilojoule per kilogram. So basically, what we have tried to do is that we do not know the exit point of the high pressure turbine. So but we already got the pressure from the first part. So the enthalpy, the corresponding entropy at this particular point should be lower than the entropy of the state point 4. If that is the case, the exit of the state point 4 will be the exit of the high pressure turbine will be a superheated stream, and we can do a further calculation based on this. So we got all the state points, enthalpies, H3 and H4, everything we have obtained, and we just need to calculate the thermal efficiency. E will be equal to 1 minus of H6 minus H1 divided by H3 minus H2 plus H5 minus H4. So that will be equal to, we just substitute the value of H3, H2, H5, H4, H6. We'll get it to be around 45%. So it's a straightforward case. What we try to do is that this is the case of a Rankine cycle with reheating. Here we try to calculate so we had to calculate the pressure at which the steam should be reheated. That is I actually use a software to get the value of the enthalpies and entropies. So you can actually look into a standard steam table. The values would not be that much different, or the appendices of a thermodynamics textbook. So usually they must be providing steam tables at the end. I use a software called Engineering Equation Solver to get these values. So in this particular problem, basically what we did is that, okay. So we needed to calculate, it's a reheat problem. We need to calculate the pressure at which it will be reheated. So that will be an altogether different pressure compared to the boiler pressure. And then we need to calculate the efficiency of the cycle. So the first point is straight away we can obtain the pressure at which 4 to 5 will take place. We know everything about the state point 6. The quality, the pressure, and based on that we can calculate its enthalpy and entropy. And that since the low pressure turbine is a constant entropy process, isentropic process, the 0.5 and 0.6 will be having the same entropy. So we know the temperature. It's given that assume the steam is reheated to the same inlet temperature. So 0.5's temperature should be same as that of 0.3's temperature, that is 600 degrees Celsius. So for 600 degrees Celsius and the entropy of the state 0.5, 6 will get correspondingly a pressure that will be 4 megapascal. And since this is a constant pressure heat addition process in the reheat process, it will be having the same pressure as that of the previous case. Throughout the process. So that is the first part of the problem. And the second part, we need to calculate the thermal efficiency, and that is a routine work. We need to calculate the enthalpies of the state points. So efficiency will be equal to work net divided by the heat input, or it could be written as the 1 minus of heat output divided by heat input. So since this is a cycle, the net work output will be equal to the net heat input. So by that logic, we'll get 1 minus of heat output divided by heat input. Heat input comprises of two parts. One is the boiler part from 2 to 3, and from there the reheating 4 to 5. We know everything about the 0.5. We need to calculate other state points. So we know about the first state point, that is a saturated liquid, and we use the pump work output that will using the specific volume multiplied by the change in pressure. You'll be getting the state point 2 enthalpy. And for state point 3, that will be at temperature 600 degrees Celsius, 15 megapascal. That is a superheated region. So you'll get that point straight away. The only nuance of this particular problem comes in state point 4. So if the state point 4, we know the pressure, the same pressure as at 0.5, because this is a heat addition process, constant pressure heat addition process. So we know about everything about the state point 4. So this pressure and the entropy will be same as that of the 3 enthalpy entropy. So we do not know whether this will be falling inside the vapor dome or on the saturated vapor line or outside. So for that, we need to calculate the entropy at state point 4. If its entropy, is lower than that of the state point 4, then that means that it should be in the superheated region. So if the entropy S3 is greater than that of the saturated entropy at the state point 4, or the saturated entropy at the pressure for 4 megapascal, that means that it should be obviously in the superheated region. And using the superheated part of the table, we calculate the enthalpy of the state point 3 using this entropy as well as the pressure. So efficiency straight away you can calculate, that will be equal to 45%. Yeah. Any questions? I didn't understand actually. Will there be classes like this again? Whether I'll be conducting the tutorial classes in the upcoming weeks like this? If that is a question, yes, I conduct tutorial sessions on every Sunday from 4 to 6. So if you have joined the NPTEL course for this applied thermal engineering basic and applied, what we could see is that every week there will be lectures uploaded in the course website, and there will be an assignment that you have to submit within a particular deadline. And to help you do these assignments, will not be solving the same problems as in the assignments, but some sort of similar, or in order to make the concept clear, we'll be doing a similar kind of problems in the tutorial session. So in the tutorial session, basically some multiple choice questions, numerical type questions, and occasionally some multiple select questions as well. And every week on Sunday from 4 to 6, I'll conduct these sessions. Oh, okay. Yeah. So that completes this problem. I'm not solving a question on regenerative cycle in this session. I'll do, in fact, do that in the next week session, the regenerative cycle problem. Because actually in the course syllabus also, regenerative cycle in the course structure also, the regenerative cycle comes in the fourth week tutorial session. So I better I'll remove that in this week's contents, which I try to. I had already mentioned at the introduction to this week's session. There are a couple of questions, couple more questions on some multiple choice questions. Look into it. Actually, if you have registered for this course, it will be automatically uploaded. So we will be uploading in the in an Excel sheet the link of the video uploaded in YouTube, as well as the slides that we had discussed in the current session. So we'll upload a PDF of that also into a Google Drive, and we'll share the link in an Excel sheet. So that will be given to the NPTEL authorities, and they would be sharing that particular link to the students who have enrolled to this course. So the video which is uploaded in YouTube, the link of it, as well as the slides which we had discussed, which I have uploaded in the Google Drive, the link of that also, that will be shared with the students who are enrolled in the course straight away. And also, if you go to the course for the course website, there will be a home page, and there also you could see. Okay, you can. Okay, fine. So I'll discuss the other set of questions, and you can access it anytime. These video lectures. Okay, if the specific steam consumption is higher, then the capital cost and thermal efficiency of the power plant will increase. Net work output and the thermal efficiency will increase. Capital cost and will decrease while thermal efficiency will increase. Net work output will decrease while capital cost will increase. So you have to actually look what is meant by the specific steam consumption. The term specific steam consumption is given as the net steam consumption rate in terms of kilogram per second to the net net power output. So basically, steam consumed, the steam flow rate divided by the work output, that will be the specific steam consumption. So basically, this is specific work only, 1 by specific work in terms of kilojoule per kilogram. So specific steam consumption is actually the reciprocal of the specific work, kilojoule per kilogram. So this will be specific steam consumption will be in terms of kilogram per kilojoule, kilogram per kilojoule. Yeah. So what you could try to see is that if the specific steam consumption is higher, that means that the specific work is lower. So more mass flow rate is consumed for the same work. That means the specific steam consumption increases. Corresponding, that means the specific work decreases. That kilojoule per kilogram work decreases. So straight away you could see is that the net, if the specific work is net power output, right? So work net. So the net work output will decrease. So this is the thing, the net work output will decrease straight away. And what will happen to the capital cost? So when the net work output decreases, that is the kilojoule per kilogram yeah, decreases, we have to use a bigger turbine or as well as a bigger pump to increase the work output. And also we have to increase the size of the boiler so that we can heat it up to a higher pressure, or use some kind of an additional fittings to regenerate or reheat the cycles. So all that is going to increase the capital cost in order to improve the network output. So once the specific consumption increases, uh, network output decreases, but our ideal objective will be to increase the network output, the specific work as so that means the specific work increases and the specific steam consumption should go down. So basically the final answer is the right one. Option 4 is the right answer. Consider the following statements regarding the reheating of a Rankine cycle. Reheating increases the average temperature of heat addition. Reheating provides wet steam at the turbine exit. Which out of the the two statements that I had just read out is correct? Only statement 1, statement 2, both the statements are correct, both the statements are incorrect. So in one of the earlier questions, we have seen the ideal purpose of reheating is to improve the quality of the steam at the outlet. That is the only thing. We can't say anything about the efficiency of the cycle, because heat input, work input increases, as well as network output increases. Net work output increases, also heat input increases. We can't say anything about the efficiency as such. It may increase or decrease. In certain cases, it can increase. So there is no surety. But the only thing that with surety that we can say is that there will be an improvement in the quality or the dryness fraction of the steam at the exit. In the case of a TS diagram, so a normal Rankine cycle will be like this. A Rankine cycle with reheating will be like this. So this is the Rankine cycle. Rankine cycle with reheating. This is without reheating. So, so with surety, what we can try to say is that the exit of the steam will be towards the right, so quality increases. So the reheating provides wet steam to the turbine. That's wrong. It provides a dry steam. Reheating will increase, will provide a dry steam. So second option is wrong straight away. Then the first part is reheating increase the average temperature of heat addition. Yes. So how could we justify that? Yeah, this is slightly controversial because you know that superheating increases the average temperature of heat addition. So if consider a case where there was no superheating. So in that case, the heat addition will be happening at this particular temperature. There is no subcooling. Take only this part. So the heat addition will be taking place at this particular temperature. And if there is a superheat, the average temperature of heat addition increases, irreversibility decreases, and chances of efficiency increasing is much higher in case of a superheating case. But in the case of reheating, what happens is that you have an average temperature here. Depending upon the reheat temperature that we are reheating into, it can actually increase or decrease the reheating. Increase or decrease the average temperature heat addition. Suppose if you are reheating it to a higher temperature, say this particular temperature, there is every chance that the average temperature of heat addition might increase. Suppose you are heating it up to a lower temperature compared to the original initial temperature. This one, maybe it's somewhere here. In that particular case, the average temperature of heat addition can come down. So the average temperature of heat addition is something that varies with respect to the temperature of the exit of the reheating process. If it is sufficiently higher, the exit temperature of the reheating process, this process, we can get a higher average temperature of heat addition and the efficiency increases, and on vice versa can also happen. So with surety, we can't say whether the reheating will be increasing the average temperature of heat addition in all the cases. So that's also wrong. So both the statements 1 and 2 are incorrect in this case. So that is an analysis for reheating. So there is no guarantee that the average temperature will be increasing in all the cases. So that completes the set of problems that we had for this week. So I'm not discussing the regenerative cycle part because that is not part of the assignment. So that can be discussed in the so in this week, basically the reheat part is the most important one as part of the syllabus. So I'm not discussing the regenerative part in this session. I'll discuss it in the upcoming week, in the next week's session. So basically, we have seen a few multiple choice questions, numerical type questions, and one multiple seller question based on the basic cycle as well as a Rankine cycle, basic as well as a reheat Rankine cycle. If you have any doubts, you can post in the course forum available in the website. We'll meet next week with the problems of the regenerative cycle as well as a modified Rankine cycles. That's all. Thank you.